If you perform an ANOVA, you need to check whether the three key ANOVA assumptions were met. And those are normality of residuals, homogeneity of variances, and independence of observations. How to do that in Python is what I'm going to show you in this video today. So let's start with the first one, checking the normality of residuals. We use normally distributed data for this example, but you can play around here to check how the results would look like for not normally distributed data. So each group here contains 30 observations. Normally distributed around slightly different means, and we combine the groups into a pandas data frame so that we can handle them more easily. And now we model the relationship between value and group. The formula here, value group, tells the model to predict value based on the categorical variable group. And we use the OLS function, which stands for ordinary least squares, from stats models to do that. And after fitting the model, we extract the residuals using this model.resid command, which will be used to assess normality. And to check for normality, we'll create a QQ plot. Now that's relatively easy. We only need these 3 lines of code here. And in the QQ plot, if the residuals are normally distributed, the points should fall roughly along this straight line here. Now, significant deviations here indicate that the data isn't normally distributed, but this is how it's supposed to look like, and in practice there's always some deviation from the perfect line here, so it's perfectly fine if there are some deviations from that line. That's what I'm trying to say here. And we can support this visual inspection because sometimes it's maybe a little bit vague, and we want to ensure ourselves with a Shapiro-Wilk test. And the Shapiro-Wilk test also tests whether or not data in general, on this specific case the residuals, if they are normally distributed or not. It's also relatively simple to do in Python. We only need to import from the SciPy stats the Shapiro package, and then we run the Shapiro function, our residuals, which is the data that we want to check whether or not it's normally distributed. And the result that we get from running this test, it's a p-value, and if that one is greater than 0.05, we can assume normality. As we are working with normally distributed data, the p-value is much larger than the 0.05, and you can use this Shapiro-Wilk test in addition to the QQ plot, in addition to the visual inspection, to test this first assumption, to test whether or not the residuals are normally distributed or not. Now let's continue to check the second assumption, homogeneity of variances. And this is also called, or maybe you have heard that under the name homoscedasticity. And to check homoscedasticity, we plot the residuals over the fitted values. So first we get the fitted values from our model, and then we plot the residuals against these fitted values. And in this plot, we look for a random scatter of points around the horizontal line at 0, like we see here. If you see a pattern like a trumpet shape, then the variances, they are not equal, they are not homogeneous. But that's all. So let's take a look at how we check or verify the third assumption, which is independence of observations. And to check for independence of observations, we plot the residuals in the order they appear in the data set or in the order they were measured. And that's also relatively simple to do in Python. We just use the plt.plot function here from the matplotlib library. We take the residuals as input, add some labels, and we're ready to go. And if the residuals display a random pattern, as they do here, then we can assume independence. And if there is a trend, for example, then they are not independent. A common example for dependent data are, for example, time series data, when you measure the same sample multiple times over a certain period. So now we've checked all the three assumptions of ANOVA, the normality of residuals with a QQ plot and the Shapiro-Wilk test, the homogeneity of variances verified using a residuals versus fitted plot, and the independence of observations that we looked at or verified with the residuals sequence plot. And only if all three assumptions are met, then the ANOVA produces reliable results. But what do you do if maybe one or even multiple of these assumptions aren't met? Well, first thing you can do is trying to transform your data, like logarithmic or square root transformation. Often that already helps. If the variances are unequal, you can use Welch's ANOVA, which doesn't assume equal variances. And if you're dealing with non-independent observations, well, you should have randomized your experimental design in the first place, but you probably have to do the whole design and the whole experiments, all the experiments again with a randomized design plan, and that's a little bit of a hassle. So make sure that you randomize your experimental runs the first place. But if you're dealing with time series data, then there is the repeated measures ANOVA or the mixed effect models that you could use instead. All right, but now it's your turn. Try to use these techniques on your own data set. Maybe watch this video next here to see how you can perform an ANOVA in Python, and then come back to this video to check the ANOVA assumptions.